All right, today we are going to talk about section 10.2. We are going to talk about properties of sound. So in the last section, we talked about how sound is regarded in pretty much the anatomy form of how our ears play a huge part in it, what a sound wave is made up of, which is a longitudinal wave, compressions, rarefactions, all things that you will need to know for the test. But in this section, we're going to talk about properties of sound. So the first thing that we need to talk about is that when you have a wave, they actually have a couple parts to it. You have something called an amplitude, which is the degree of disturbance from a wave. And the amplitude is related to how close the particles of the medium are together in the compressions. So this is specific for longitudinal waves. And when you have the amplitude increase in the longitudinal wave, this is actually going to push the particles in the wave together than they would if they were not having more than if they were in rarefactions. So again, one important term is the amplitude, which is in a longitudinal wave related to the compression of the wave. So this is when they are super close together versus more spread out, and the particles will be closer together as well. So in this image, we can see that the amplitude is right here. So this is how kind of going from top to bottom. So you can also see in this image here, it shows you between a wave and also shows you particles. So in the wave, you can see how the amplitude of the wave is a lot higher and it's closer together than in the lower amplitude. And then in the higher amplitude particles, you can see how they're more like closer together versus in the lower amplitude, they're more spread out. Okay, so in order to have a sound wave with a high amount of amplitude, you need a lot of energy that has to be transferred from the object that is vibrating to the medium that the sound is being transmitted through. So remember, medium can be a solid, it can be a gas, it can be a liquid. So in order to determine how big the amplitude is, you really have to study the energy that's being transferred from the object that's vibrating through the medium that it's traveling, the sound is traveling through. So for example, if you're turning the volume on your phone, so if you're turning the volume on your phone, you're going to be decreasing the amplitude of the music that you listen to, okay? So basically, when you have different amounts of, volume or, you're controlling that aspect of whether it's a stereo, radio, or whatever, you're controlling the amplitude of the waves of music as well, or the sound waves that's coming through it. Another important thing to remember is that amplitude is actually related to the intensity of the wave. And we're going to learn about what exactly is intensity. So intensity is the amount of energy that passes through a certain area, so a specific area, in a specific amount of time, okay? So if I had some kind of stereo, so say this is my speaker, and I have this area right here that I'm kind of zooming in, whatever is coming out of this area here, the amount of energy coming out of this area here in my box at a specific time would be how I would measure intensity. When you turn down the volume on your computer, you can also reduce the amount of energy that's going to be carried through the sound waves that's coming out of the computer speakers. Therefore, you are reducing the intensity that's coming out. This is the same thing with when you're turning down the volume of your phone. You're reducing the amount of amplitude, therefore it's quieter music, therefore you're reducing the amount of intensity as well. So another example is this person is looking at a screen. So the amount of energy coming out of this specific area at a specific time would give you the intensity for the sound waves being emitted. Okay, intensity influences how far a sound can be heard. So whether you are whispering or shouting, you are going to have a difference in intensity because one, if you are farther away, you are going to have less sound intensity. So, a person who's farther away is heard to be softer than if you were closer to the source, then it's going to sound louder. So if I'm, speaking on one end of the soccer field to the next, and you're standing on the other side of the soccer field, if I'm talking to you, it's not going to be as loud or heard as loud as if you were right next to me. So intensity does have to deal with how the distance of the object that is receiving the sound. The energy that a sound wave carries spreads out as the sound wave spreads out. So the more a sound wave is spread out, so is the energy going to be spread out. So if the blue thing that I just drew is a sound wave, the more spread out it is, the more the energy is going to be spread out. The energy that is being carried in this sound wave can also be converted to another form of energy known as thermal energy. This is also known as heat. And so the more farther the sound travels, the more energy is going to be converted to thermal energy. So now let's talk about loudness. So some sounds are super loud and they can be pretty hard to hear and hurt when you hear them, whether it's super high pitched or just super duper loud. If you've ever been to a concert and you go closer to the stage, like for me, my ears are sensitive, so it really hurts. Or if you've ever heard like feedback or something that's super high pitched, that can hurt your ears as well. But loudness is how we as humans perceive sound volume. And it depends on the intensity of the sound. So again, loudness is how humans perceive the sound of volume, and it depends on the intensity of the sound. So remember, intensity is how much energy in a specific area at a specific time. Okay, so when sound waves of high intensity are coming and reaching your ear, they can cause your eardrum, remember, which we said was the end to your outer ear, start of your inner ear. It will cause your eardrum to vibrate by going back and forth as your eardrum literally starts to move. And when this eardrum starts to move, the sound wave starts to move from the outer ear into your into your middle ear and then into your inner ear. And this also depends on the intensity of the sound wave. So when you have your eardrum moving back and forth, the greater distance than a sound wave of low intensity can actually reach your ear. Meaning, when your eardrum is moving back and forth, depending on the amplitude or the intensity of the sound wave, it will depend on how much your eardrum is going to move back and forth, and that will determine how much interpretation or how loud the sound wave is actually how loud it actually is, and therefore it will actually it will be able to be interpreted by your brain as a loud sound or a quiet sound. So here's a kind of like a line, like a chart or a graph that tells you how loud certain things are. So loudness is measured in decibels. If you hear 20 decibels, around 20 decibels is the rustling of the leaves, which we can hear. On a windy day, you can hear the rustling of the leaves. Close to that is a purring of a cat. So those things are pretty quiet. In the middle, you have maybe a high school cafeteria, just a bunch of jumbled voices. And then around 110, you have a rock concert, which is pretty loud. And then very close to that at 120 is pretty much your pain threshold. Anything after this, between 120 and 150 is super painful for your ears. And so this 150 is like you're right close to a jet plane that has its motors running and it's ready to take off. And it can be pretty painful. So you always want to be careful when you're going to a rock concert, because if they are increasing the decibels in their sound, it can actually damage your hearing. So what is decibel? It is a unit of sound intensity, also abbreviated as lowercase d, uppercase b, like this. And depending on the type of person you are, you may be sensitive to some decibels, like that are, lower, while someone, if you're sensitive to, say, a decibel around 55, somebody else could be like, oh, that's nothing to me. Or to other people, they could be like, wow, that's super loud, but you're like, no, it's not. So it really depends on person to person how loud something is. No one's going to have the same scale on what they determine to be loud. Now, every increase of 10 decibels on the decibel scale is going to be a tenfold increase in the intensity. Tenfold meaning 10 times more. So for example, if you have 30 decibels and you're increasing it to 100 decibels, you are saying that 100 decibel is also equal to 10 to the 7th power, which also equals 1 million decibels. Okay? Why? How do we get that? Well, first, you're going to take the 100 subtracted by the 30 to get 70. You're going to divide 70 by 10 because that's the decibel that it's increasing by, and you're going to get 7. That is going to be your x, which is your exponent. So then when you do 10 to the 7th, that equals 1 million. Okay, so the decibel scale. When you have a sound that is super low in decibels, say about 0 decibels, you can't usually hear this. That's a very, very small amount of sound. But if you have something over 90 decibels, that can actually cause permanent hearing loss in a lot of people. And remember, permanent hearing loss is when you have the hair cells in your cochlea are being destroyed. They don't grow back once they are. There are also some sounds that can be really short but super sudden, like if you're walking by a construction site and something falls, or concerts, and that can go up above 120 decibels, and that can cause a lot of pain and also permanent hearing loss, okay? Ways that you can prevent this is wearing earplugs when you are going to, say, concerts, or if you're walking in areas that you know have loud construction, because your ears are very sensitive. One of your most sensitive parts of your body are your ears. And so you want to make sure that you're providing them with good protection so that you don't result from permanent hearing loss, which can happen from just a very spontaneous loud sound. There's another term that we need to talk about when we talk about sound, and that's pitch. So pitch is usually related a lot of times to music. If you've ever watched Sound of Music, you might have known like the song "Doe, a deer, a female deer." But a lot of people who study music, they have to learn the basic, which is a musical scale, and that's the do, re, mi, fa, sol, la, ti, do. And as you start to, sing this musical scale, you're going to notice that your voice is going to become higher and higher and higher as you go from this do to this do. So as you sing, you are actually experiencing a change in pitch as you go from the first do to the last do, which is going to be a lot more higher. So a pitch definition is how high or low a sound is going to be or seems to be. When you're on the right side of a piano, that has a higher pitch than the left side of a piano. And this is related to the frequency of the sound wave. So we said amplitude is related to the intensity of a sound wave, but a pitch is related to the frequency of a sound wave. So let's see more about that. So what is exactly a frequency? A frequency is when you measure how many wavelengths. Okay, so remember, if I have a wave like this, a wavelength is from here to here. So a frequency is saying how many of these wavelengths are going to pass through a particular point at each second. When we talked about longitudinal wave, we said that that was a sound wave. So the frequency of a longitudinal wave is the number of compressions, remember when they're super close together, or rarefactions when they are spread apart, that pass by each second, okay? And this is going to be measured by something called hertz. 1 hertz equals 1 wavelength that is being passed per second. So if we're looking at this wavelength right here, we're saying how many this 1 wavelength is going to be passed in a second will equal 1 hertz. All right, so make sure you know that a frequency is a measure of how many wavelengths are passed at a particular point every second. Longitudinal wave, aka a sound wave, is a frequency, is a number of compressions and rarefactions that are passing also each second, and it's going to be measured by hertz. If you have high frequency, a high frequency sound wave is going to send a lot of compression, so close together sound waves to your eardrum. And this is going to happen literally every second. So, and as these sound waves are being sent to your eardrum, it's going to cause the eardrum to vibrate more and more and more. Then if you had a low frequency sound wave hitting your eardrum. So the lower the frequency the sound wave is, the less vibration is going to occur. The higher frequency you have a sound wave, the more vibrations you're going to have. And the brain is going to take those high frequency sound waves and view it as a high pitch. Because remember, pitch and frequency are related to each other. All right, so your brain will take that high frequency of the sound wave and convert it to a high pitch. If you have a decrease in sound wave frequency, then you will also have a decrease in pitch. So increase in frequency equals increase in pitch, or decrease in frequency equals decrease in pitch. They go hand in hand. Now, a human teenager, right, so you guys, you can hear between 20 hertz to 20,000 hertz, okay? But as you grow older, you're going to not have that wide of a frame for what you can hear. It's going to decrease as you get older. We as humans, right, not just teenagers, but humans in general, are sensitive to sounds between 440 hertz and about 70,000 hertz. If you could notice, this is not really, 70 hertz is a lot higher than what a teenager can experience, okay? But these are examples are, dogs, they can actually hear up to 35,000 hertz, so not as high as a human. Bats, they can hear up to 100,000 hertz. So they have very, very sensitive ears, bats do. Dogs, they can hear, but not so much. Now we're getting into something called the Doppler effect. This is a really important effect that we will be talking about when it comes to moving sounds or moving sources of sounds versus an observer that's standing there. So like if you are standing on the side of the road and you hear an ambulance coming towards you, why does it sound different than when the ambulance is going past you? So let's take an example for a racetrack. Say that you're standing at the side of a racetrack and you have a bunch of cars that are driving by. When the cars are coming toward you, the pitches that they are making from the car, from their engines, are going to sound higher. When the car is moving past you, it's moving away from you, the pitch that's going to be coming from their engine is going to sound a lot lower, okay? I'm going to say this again. You're standing at a racetrack, you have a really fast car coming towards you. That pitch from that engine is going to sound a lot higher than once it has passed you and is going away from you. It's going to sound a lot lower. And this is called the Doppler effect. This is when you have a change in the wave frequency because you have a wave source, right, which would be your car in this sense, that's moving relative to the observer, which is you. And now you're comparing the wave source plus the observer and seeing how does that affect what I hear and the intensity of the pitch that I'm hearing. This can also happen when the observer, which is you, is moving in relative to a wave source. So say, for example, you are moving and the car isn't, or the car is moving and so are you moving. So this could be like when you're driving on the highway and you have an ambulance passing by you, or a really loud car with a loud engine passing by you. Those things can also be considered under the Doppler effect. So it's not always going to be when you're not moving. You can be moving and still experience a Doppler effect, whether the source is moving or not. Okay, so here we see an example of a car that is racing. We see that it's letting out a compression, which is like a sound wave, as it continues to move. In the next picture, we see that compression A has now moved all the way out here, and another compression is being released called compression B. As compression A and as compression B are close together in the front of the car right here, the observer is going to hear a high-pitched sound. But if you can see back here, the compression B and compression A are more spread out. And therefore, when this car passes, he's going to hear a lower pitch sound. Now, Doppler effect can occur when the source of the sound wave is moving relative to the listener. So this is like saying if you're standing here and you're not moving, but you have some kind of car. Yes, you're welcome for my wonderful car. And the car is moving. When the car comes towards you, you're going to hear a high pitch. And then when the car has made it farther away from you, you're going to hear a low pitch. When you have a moving sound source, so you yourself are not moving, but the sound source, so whatever is producing the sound is moving, you're going to have compressions that are closer together as the observer are observing the sound. So the frequency is going to be higher and the observer is going to hear a high pitch. So this is like an ambulance. If it's approaching you, you're going to hear a higher pitch than if the ambulance is driving away from you. Compressions that are close together cause a higher pitch sound than when they're further apart, which is literally what I just said. So if the ambulance is coming towards you, you're going to hear a high pitched sound. When the ambulance has passed you and is going away from you, you're going to hear a low pitched sound because of how close the compressions are together. So you're going to have close compressions here, therefore producing the high-pitched sound, and you're going to have farther compressions here from each other, which is going to produce a low-pitch sound. So now let's talk about moving observers. So say that you as the observer are actually moving. So when this happens, the sound will be louder and the pitch is going to be higher when you as the observer moves closer to the sound. But the pitch will be lower as an observer moves away. So if you have a fire alarm that's going off like crazy, if you're coming towards the fire alarm, you are going to hear it louder and you're going to hear a higher pitch because you as the observer are moving. If you are moving away from the fire alarm, it's going to sound lower and it's going to obviously get quieter as you move away. And this is when you have the observer moving, not the source. The fire alarm is a source and you as the observer, you are the observer. And then this is you walking away. We also have something called electromagnetic waves in effect with Doppler effect. So this is when the frequency of the electromagnetic waves changes if you have an observer and a wave source that are moving relative with each other. So this is when you and whatever source is producing the sound are moving. So this can be stars that are like moving in space, okay? These are what is producing these electromagnetic waves. And these are what will cause the electromagnetic waves to actually change. So police actually use the Doppler effect in the radar as they, are catching people who are speeding. So what happens is they send waves towards a moving car with their little device, which will reflect from that car and tell you what speed that car is moving depending on the frequency that they receive back on the device. And this will actually tell them what speed you're going at, and they can decide whether they need to pull you over or not. So again, the radar that they have in this device, it will send sound waves towards a moving car. It will hit the moving car and reflect back from the car. And the frequency that they receive back from the reflection will tell them what speed and also the direction that they're moving in, which can determine if, they're above the speed limit or not. Okay, so let's do some questions that are in your packet. For a sound with a low pitch, what else is also always low? So we said amplitude goes with intensity and frequency goes with pitch. The amount of energy that a sound carries decreases when which increases? Give you a second to answer that. The amount of energy that a sound carries decreases when which decreases as well? If you said amplitude, you are correct. Sound waves with the same pitch and loudness traveling in the same medium may differ in which property? This one is going to be quality. We didn't really talk about this. We'll talk about this in the next section. All right, so now that we finished chapter 10.2, we are going to do a quiz review to review what you will need to know for the quiz. So first of all, amplitude we said was related to intensity. So remember, if I have a wave, this is going to be my amplitude. And intensity is the amount of energy coming from a specific area at a specific time. If you have a greater amount of amplitude in a sound wave, you have to have more energy that is going to occur between vibrating objects, okay? So more amplitude, you will have more energy that will occur between vibrating objects. If you have a wave disturbance, right? So basically more of a wave, you're going to have a correlation with the amplitude of the wave. So this is more of a disturbed wave than this. Therefore, you would have a higher amplitude or more amplitude in that wave. The intensity is the amount of energy that is transferred across a certain area at a specific time. So this is what I said before. This is the definition of intensity. So make sure you know that. If you need to pause the video to write this down, please do that. We also said that the intensity of sound is measured in decibels. Every 10 decibels, or dB, is going to increase by 10 to some exponent. And we did a sample problem of that in this section. So if you need to go back to that and watch that, you absolutely can. But remember, they're going to increase by 10 decibels or 10 to the xth power. When you have a high intensity sound wave that is going to reach your ear, that means you have particles of air that are vibrating so fast that they are hitting your eardrum with a great amount of force. So when this is happening, your brain is getting these impulses and they're interpreting these vibrating sounds as loudness. That's what we perceive as loudness. Loudness also depends on intensity. And when we as humans are perceiving pitch, like do, re, mi, fa, sol, la, ti, do, right? You're going from do to do, but you're increasing in pitch. That means that you're also increasing in frequency because they are related to each other. So increase in pitch is going to give you an increase in frequency. Your brain will take that high frequency that is coming through your ear and interpret it as a high pitch. You guys as teenagers, remember this fact is that you can only hear up to 200 hertz in pitch. As you get older, you will become sensitive till you reach to it, about 70,000 hertz. And then you will start to lose that as you get as you age. So an older person, maybe in their 60s are not going to hear as well as somebody who's in their 30s. And that's it for our section 10.2 quiz review. Remember, if you need to pause and copy this stuff down, you can pause this video at any time. Make sure you study all this information for your quiz, and good luck.